Hello once again, and welcome back to a crash course in formal logic. This time we're going to study natural deduction systems and propositional logic, a very effective way of proving validity of arguments without doing truth tables of the direct or indirect sort. Now, an inconvenient truth is that truth tables can get very long if there's too many simple sentences involved. And we saw an example earlier that involved 4 propositional variables. We wound up with a truth table that looked like this. Notice once again I've highlighted all the premise columns, and I've also highlighted in the orange where the conclusion turned out true or false. We had to get down to line 16 before we could invalidate the argument. Now you may think that we can solve this problem by going with indirect truth tables, and we found that that was an effective way for handling the argument that we just looked at. What we did was we tried to see how we could be forced to try and figure out a way in which the premises could all be true and the conclusion still turn out false. And if we could find that, then we invalidated the argument. And we found precisely the row on the truth table, the row where A, R, N, and C are all assigned false, in which we would have invalidated the argument on a direct truth table. But there's another important fact. Indirect truth tables can get very long if the conclusion is very complex. Notice, I'll just make this conclusion a lot more complex and try to imagine how you would even set up or begin your indirect truth table. You'd have to find all the ways in which this conclusion could be false. It's just not an effective system. So there has to be a better way, and the better way is a natural deduction system in propositional logic. Now, what is natural deduction? Natural deduction is a method for establishing validity of an argument by moving from premises to conclusions through steps. And the steps in the proof are going to be justified by rules of inference. We're going to study 2 broad categories of rules of inference. Notice, we're still going to need truth tables to prove invalidity of arguments, and sometimes the indirect truth tables are the best way to go for that. But to prove an argument valid, natural deduction is the way to go. So basically you're going to start with premises, and instead of moving towards the final conclusion directly, you deduce an intermediate conclusion and maybe another intermediate conclusion, and use the both of them to derive the final conclusion through a rule of inference. For example, if I take A or B tilde A, then I can deduce an intermediate conclusion. Namely, I could deduce that B must be the case. And if I took the premise tilde C dot D, well, clearly if that's the case, then tilde C has to be true, and I deduce from those 2 intermediate conclusions that tilde C dot B is the case. That's the general idea, but we need rules to justify those blue arrows and which moves are appropriate and which are inappropriate or invalid. So in order to get our natural deduction system rolling, we need to prove, we need to show which steps are going to be justified and by which rules of inference they will be justified by. There are 2 broad categories of rules of inference. The first are the rules of implication, and that's where you derive a new line or step in your proof from 1 or 2 of the previous lines that imply it, and the rules of replacement. They permit derivation of lines or steps in a proof because basically the new line or step says the exact same thing. It's logically equivalent to the information in one of the previous lines. One way to think of it is that implication is a one-way street. When you move from 1 or 2 lines in a proof to something that's implied by them, that implication may go one way but not in the reverse. When you have equivalent claims, well, you can go back and forward either which direction. For example, if I have A dot B, well, that logically implies A, but you can't move from the claim that A and just arbitrarily move to the claim that A dot B is true. However, if you have the claim A dot B and you move to the claim that B dot A, obviously those say the exact same things. You can move back and forth between them. That's an equivalence. Or if I take, looking back up at our gray signs at the top, A is equivalent to B, and I have another premise that says tilde A, well, obviously, since A and B take the same truth values, I should move down the road to the claim that B is false. But from the claim that B is false, by that claim alone, I can't go the reverse direction and move to any claims about A without the help of other premises. So we're going to study these 2 rules of inference in detail. We're going to start in this lesson with the rules of implication, and we'll move to the rules of replacement in another lesson. Now, the fact of the matter is, there is no substitute for just simply memorizing the rules. So get out your memory cap and get to work. Initially, the memorizing is tedious work, but the good news is the rules are very intuitive. The hardest part is sometimes just remembering the names for the rules. Once you get the memorizing done, it's going to pay off for you in the long run. And the other good news is that most textbooks use the exact same rules and typically the same names for those rules. I've used Patrick Hurley's textbook a lot and Mary Lee Salmon's textbook, A Standard Introduction to Logic and Critical Thinking. Another one that I've used is Copey's Introduction to Logic, and also kind of like Godel Carter's book, An Introduction to Logic. And for more advanced courses, I've taught modal logic out of Kenneth Conondike's book. I can tell you this much. All these books use nearly the exact same rules and nearly the exact same names for all of them. You're not going to find much deviation in logic textbooks. So let's study the rules of implication first. We're going to study 4 of the harder rules, and then I'll get back to 3 of the simpler ones. Now, Cicero was a famous Roman orator who said he wasn't very impressed with logic. He said that he thought his dog could do it. He's thought his dog had mastered the disjunctive syllogism. If a dog is chasing a rabbit down trails and he loses sight of the rabbit and he sees a fork in the road, the dog can sniff down one trail, and if he doesn't catch the scent, immediately charge off without sniffing down the other. Cicero thought that that meant that he was mastering the concept that if P or Q is the case, then if you knock out P, that leaves only one option left, Q. The dog mastered disjunctive syllogism. I'm pretty sure we can all master it then. But it has very many forms, and you have to be a little bit proficient in logic to see that the following example is another example of disjunctive syllogism. The second premise basically put a stopper on the very first disjunct of the first premise. That just leaves one option remaining. This is also a version of disjunctive syllogism at work. We'll take this example. It doesn't matter which order the premises are in. If the disjunctive premise comes second, then as long as one premise puts the splotch on one of the disjuncts, well, there can be only one disjunct remaining. And this can get kind of complex sometimes. Notice I've got an example here in which we have tilde b as a disjunct, and then a long complex proposition after it as another disjunct. And in the second premise, I have double negation at work. Well, I'm still denying the first disjunct of the first premise, and that still leaves only one option remaining. Again, that's another version of disjunctive syllogism. It works in all these cases. Well, time to move on and study another rule of implication, the hypothetical syllogism. We've studied syllogisms before, categorical syllogisms. Hypothetical syllogisms are a bit different. The hypothetical syllogism says that if proposition P takes you to Q and proposition Q takes you to R, P is sufficient to get you to R after all. That may remind you of how we studied category logic. But basically what we have instead is a situation where P is connected to Q and Q is connected to R, so in a sense P is already connected to R, only now we're dealing with propositions instead of dealing with categories as we did before. Now take a look at this example. A implies a conjunction, and that conjunction implies tilde H. Does it follow that A is sufficient to take you to H? Yes, it does. You still have that middle proposition, that hookup term between A and H in these examples. And that's basically what's doing your work, getting you the proper link up between A and tilde H. Well, we can try this example on for size. Notice that tilde M is implied by one proposition and tilde M implies another proposition. Consequently, that makes tilde M a good link-up term between the propositions in question. We can tell from these two premises that the disjunction of C and K leads to the disjunction of R and S. Or take an even longer example. Can you find the link-up term here? Well, I'll help you out a little bit. It's right here. L implies N. There's no rule that says that a horseshoe claim cannot be the sort of middle proposition that links up two other propositions through hypothetical syllogism. And the two propositions thus linked up are like so. All examples of hypothetical syllogism at work. Now be careful not to confuse hypothetical syllogism with this invalid version thereof. If P implies Q and R also implies Q, that tells you nothing as to whether or not P and R imply each other just because they have a common implication. Try this example on for size. If Bill Gates is a man, then he's a human being. And if he's a woman, then he's a human being. Two propositions that both imply that he's a human being. Does it follow that if Bill Gates is a man, then Bill Gates is a woman? Not even by a long shot. So I don't think Bill Gates would fall for this sort of reasoning, and neither should you. So let's move ahead and study Modus Ponens and Modus Tollens, two very important forms of argument, two very famous forms of argument, and their Latin names. Don't let them intimidate you. Modus Ponens literally means a mode or a way of building up. These are asserting mode. Take this for example. 12 million children die yearly from starvation. Something is wrong with food distribution, and they are dying yearly from starvation. Move to the conclusion, something is wrong with food distribution. The way this argument worked is I took a premise that involved a horseshoe, and I affirmed the antecedent of that horseshoe, thus allowing me to move to the consequent thereof for my conclusion. Basically, that's simple. And there are various ways of doing this as well. For example, I could bring in tilde f implying a biconditional. Again, the idea is to affirm the antecedent and then move straight down to the consequent as your conclusion. As long as you do that, you will have a valid form of inference. And it doesn't matter how complex the argument is either. Notice once again, I have a horseshoe claim, an implication claim as my first premise, and I have something that affirms the antecedent thereof. Again, you have to remember, take the entire consequent of that conditional and move it straight down into your conclusion section. Or try this on, for example. K dot L being our first premise, well, the order of the premises don't matter. What matters is the second premise has the horseshoe as the main connective. Again, affirm the antecedent and move to the entire consequent for your conclusion. As long as you do that, it's always a valid inference. So in short, modus ponens means affirming the antecedent. Now be careful for an invalid argument. Looks like modus ponens, but it's not. If Napoleon was killed in a plane crash, then Napoleon is dead. And Napoleon is in fact dead. Does it follow that Napoleon was killed in a plane crash? Not by a long shot. The problem is, I affirmed the consequent rather than the antecedent of my conditional sentence. Affirming the consequent is a formal fallacy, a very famous one. And the example that we just looked at does exactly that. When you spot these formal fallacies, you know an argument's always invalid. Just to give you another example, if bats are birds, then bats would have wings, because birds always do. And bats do have wings, so do you want to conclude that bats are birds? Well, we know they're not. They're mammals, of course. Notice the problem here is not the truth or false, the truth of the premises. Both of the premises are true. It's that we made a bad inference by affirming the consequence. We did modus ponens incorrectly. I like to do a little exercise called proving the ridiculous. This is a lot of fun. There is nothing so ridiculous that you cannot derive it from all true premises if you're allowed to get away with affirming the consequent. And that's a pretty good demonstration of the fact that affirming the consequent is a very bad form of inference. So I challenge you to find a ludicrous proposition and then prove them, quote unquote, to be true using all true premises and by affirming the consequent. It's amazing how often you can do this. Well, just to prove my point, let's use a few examples. How about proving that Tom Cruise is God Almighty? Or how about that I'm over 10 feet tall? Or how about that President Obama was born on Mars? You think we can't prove these? If you let people affirm the consequent, they'll prove it every time from all true premises. How about this? Tom Cruise is God Almighty. Don't believe it? I'll prove it. If Tom Cruise is God Almighty, he can certainly tie his own shoestrings, right? Well, if God can part an ocean, then he can certainly tie his own shoestrings. And we know that Tom Cruise can tie his shoes. So, what does that prove? It proves absolutely nothing, unless you try to get away with affirming the consequent. How about I'm over 10 feet tall? Think we can prove that? Well, if I was over 10 feet tall, wouldn't you have to agree that I'd be over 4 feet tall? 10 is bigger than 4. And I'll let you know this much about me. I am over 4 feet tall. Does that prove anything? If you affirm the consequent, you'll get a ludicrous conclusion out of these two premises. Or how about President Obama was born on Mars? Don't believe it? I'll prove it by affirming the consequent. If a President Obama was born on Mars, then he was born within 1,000,000 light years of New York. That has to be true. And Obama was, we know, born within 1,000,000 light years of New York, wherever on Earth he was born, he would be born within that distance of New York. So what does that prove? Absolutely nothing. Affirming the consequent is a bad form of inference. Now let's talk a little bit about Modus Tollens. Modus Tollens is the way of denying, the way of tearing down, just like Modus Ponens is the way of building up. If Japan cares about its endangered species, then it stopped killing whales. It has not stopped killing whales, so it apparently doesn't care about endangered species. So what I did here is I took a horseshoe claim and I put a stopper on the consequent. I denied the consequent with my second premise. Consequently, I was able to also deny these conditions sufficient to get us to that particular consequent. What matters here is that anytime you have a conditional sentence and another premise that denies the consequent of that conditional sentence, then you're entitled to say the sufficient conditions to get us to that consequence could not have been met. That happens even in cases such as the example over to your right, in which you're dealing with some pretty complex stuff. I'm dealing with double negation in this particular case, but I did deny in the second premise the consequent of the conditional in the first premise. What does that mean? I can move to the negation of whatever was sufficient to get us to that consequence. Notice I'm putting a tilde in here. That is a very important step, even if I have to do double negation to get to it. Or take a look at the example on the bottom. The second premise is a very long conditional sentence, but there is the first premise that denies the consequent there. So if you deny the consequent, take the entire antecedent, do it as a conclusion, making sure that you put a negation on it to show that it cannot be the case. So in short, Modus Tollens basically means denying the consequent. That's another way you can think of it, or the way that you can name it. Now, just like there's an imposter version of Modus Ponens, there is an imposter version of Modus Tollens. Let me illustrate. If Napoleon was killed in a plane crash, then Napoleon would be dead, for sure. But he was not killed in a plane crash. Well, does it follow from that Napoleon is not dead? Not by a long shot. That's just one of many ways that Napoleon could have died. Basically, what we have going on here is denying the antecedent instead of denying the consequent. That's bad. It's another formal fallacy. So watch out for situations in which a person tries to do what you see over to your right here. That is, putting the stopper on the antecedent rather than the consequent. The consequent lists necessary conditions for the antecedent. So if those necessary conditions aren't met, then the antecedent can't hold. But the reverse is not true. Well, this might be another good point to play a game of proving the ridiculous. You remember the rules of the game, right? We tried to show how bad certain bad argument forms are by finding the most ludicrous propositions we can and then quote-unquote proving them to be true using only two premises and showing that we can get to that conclusion if we're allowed a bad argument form. How about this for a bad conclusion? Bullets cannot harm me. Well, I'll bet you money that they can. Let's prove it by denying the antecedent. And while we're at it, how about this? Logic education is not a worthwhile endeavor. I think that's a pretty ludicrous proposition, and I hope by this point in the series you agree. Well, all I need is this conditional premise. If bullets can give me lung cancer, then bullets can harm me. Well, and all of you know that's not the way that bullets go around harming people. But if I point out the fact that bullets can't give me lung cancer, Am I allowed to move to the conclusion that bullets can't harm me? Not by using good rules of inference. Or consider this, logic education is not a worthwhile endeavor. Well, I know one way it could be a worthwhile endeavor. If logic education could help me win the lottery, it'd be a worthwhile endeavor. Unfortunately, it can't do that. But if it can't do that, does it follow that it's not a worthwhile endeavor? No, that's the fallacy of denying the antecedent. So notice, what makes this all confusing is that all four argument types, both modus ponens, modus tollens, and their imposters, start with the premise P implies Q. Both the good and the bad argument forms start that way. So it's very important to distinguish the argument types in the green boxes here from the ones in the red boxes. And the difference is, the good types of arguments and the bad type involve very different forms of argument. Take modus ponens. It starts from a premise P implies Q, but it tries to reach the conclusion that Q. You're going to be perfectly fine if you've got P to carry you along across that horseshoe headed the right direction. No problems with that. The problem is when you try to get to a different conclusion using this exact same premise that P implies Q. By way of contrast, if you tried to get to the premise that P, by affirming the consequent Q, then you're headed in the wrong direction. And that's a recipe, I'm afraid, for, well, logical disaster. A similar thing happens when you're dealing with modus tollens, except in that case, you're dealing with negations. What I mean by that is that as long as you're trying to get to the conclusion that tilde P by denying the consequent of your conditional sentence, well then that's a safe inference. You're going to travel just fine with that. But if you try to go the opposite direction, say you try to reach the conclusion instead of tilde P that tilde Q is true instead, well, you're not going to be able to do that with tilde P. You're headed in the wrong direction, and you're going to get the same result, bad argument and bad logic. So these arguments are very distinct. You need to memorize the four types and how to use them and how to avoid the incorrect types. Now we said that natural deduction works when you use premises to reach intermediate conclusions and then use those intermediate conclusions to deduce your final conclusion. Let's use our four rules of inference that we studied in order to do that. Let's go ahead and try this derivation for practice. How about we have a premise that says A or B is true and tilde C implies tilde A, C implies D, and tilde D is true. Let's try to reach the conclusion that B. You notice that B only occurs in the premises up there in premise number 1. It sure would be helpful to have tilde A to use a disjunctive syllogism to reach B. But in order to get to tilde A, we have to somehow affirm tilde C. We can get to tilde C if we can use 3 and 4 to do modus tollens. Once you lay out a strategy, start laying out your proof. Tilde C follows from 3 and 4 by modus tollens. Tilde A would then follow from 2 and 5 by modus ponens. And finally, we could get B by using line 1 and line 6 by disjunctive syllogism. You just take it step by step, and you get your proofs rolling like this. Now let's try another proof. How about E implies that K implies L, F implies that L implies M, G or E is true, tilde G, and F. Therefore, K implies M. I'm going to have to lay out a strategy here. Look at all these propositions. Aren't you glad you're not doing truth tables for this argument? Well, first step is we need to get, if we want to get to K implies M, we got to get to the consequence of both premise 1 and premise 2. So we have to find a way to affirm E and affirm F. Well, F is already given to us, so that's not going to be a problem. To get to E, we'll have to use 3 and 4 by disjunctive syllogism. So let's go ahead and get E by 3 and 4 disjunctive syllogism, and then we'll get to K implies L using 1 and 6 modus ponens. Once we got into K implies L, we can get L implies M, since we already have F in premise 5 that affirms the antecedent of 2. Once we have those two, simple hypothetical syllogism is going to get us to K implies M. It's really easy when you just lay out a plan. Well, I've got 3 more rules of inference for you. This is going to be a longish lesson. You're probably thinking that logic is going to be quite a drain. Trust me. The point is, I'm going to obey the old acronym KISS. KISS just means keep it simple, stupid. The remaining 3 rules are extremely intuitive. You're not going to have any trouble memorizing them. The three rules that we're going to study are conjunction, simplification, and addition. They are very easy and intuitive rules. You're not going to have any trouble remembering these. So let's start with the conjunction rule. If you have a P and a Q, can't you put a dot between them and reach that as by way of inference? That seems pretty obvious you can. You can do it with more complex propositions as well. For example, if E and tilde E and tilde G are true, just go ahead and put a dot between them. You're allowed to reach that by rule of inference, conjoining any two previous premises that you had, basically. Or take these two. Now, you can conjoin them, but you got to make sure and put parentheses in their proper place. Otherwise, you're not going to end up with a well-formed form. Sometimes you're going to have to get even more complex and just put brackets around the two propositions in question in order to keep your conclusion, or that intermediate conclusion that you reached, as a well-formed form. So remember, the only thing complex about the conjunction rule is you have to remember where to put parentheses and brackets to make sure you end up with well-formed forms. Otherwise, it's perfectly intuitive. And simplification is another rule that applies to the dot. If you have a conjunctive claim, you can move to the truth of one of the conjuncts. And it works with more complex propositions as well. Just eliminate one of the conjuncts and move to the other by way of inference. It just works that easy. After all, if both conjuncts are true, even in a complex proposition like this, you should be able to eliminate one and reach the other as a conclusion. Remember, when you're eliminating one, you're not calling it false. It's not false. But you don't want to have that in your arguments. You want to have a way of simplifying things, and consequently, this rule comes in really handy. Now remember, in this case, as opposed to the last rule, you sometimes have to remember when to eliminate brackets that are unnecessary once you've simplified a proposition. And watch out for one more thing. There are some textbooks that are very strict and say that you can only simplify to the first conjunct. Obviously, we know it would be equally valid to simplify to the second. Some textbooks just don't allow it. So check whichever textbook you're using. So if you do have a textbook that tells you that when it comes to simplification, you got to take the first and leave the rest, then I suggest following your textbook's advice. Now we have rules for introducing and eliminating both dots and wedges at this point. To eliminate a dot, we use simplification. To introduce it, we use conjunction. And to eliminate wedges, we use the disjunctive syllogism that we studied earlier. It's all that's going to do it. But to introduce a new wedge claim in the course of an argument, what do we use for that? Well, we use something called addition. Because the rule for the wedge is so generous, really, if you have any premise that's true, you can really wedge off from that premise to anything, whether it's true or false, and you end up with the correct inference. For example, if tilde f is true, well then it should be the case that tilde f wedge, I don't know, any old thing, this biconditional, for example, is true. The one thing you have to remember with addition, sometimes when you use it, you have to take whatever you're wedging off from and you have to put parentheses around it. That's just a way of maintaining well-formed forms. Sometimes you even have to use brackets, like in the case of this last example. But as long as you remember to use your brackets and wedges, or rather parentheses, to maintain well-formed forms, you can construct all sorts of disjunctive claims you need in the course of a proof. So just remember your parentheses and your brackets to maintain well-formed forms, and then what can you do? Well, you can dive or wedge off without fear to any old proposition that you want. The inference is going to be a valid one. So, I promised you 3 new rules, all explained simply. They don't get any more simple than the last 3 rules we studied: conjunction, simplification, and addition. First of all, let's start off with the premise that says H or tilde B implies R, and H or tilde M implies P. We have H. Can you get to R and P? Obviously, you're going to want to use modus ponens combined with your new rule of addition for the wedge. So I'll just introduce what I need to affirm the antecedent of premise 1, and I'll introduce what I need to affirm the antecedent of premise 2. Addition will give me both of those straight out of premise 3. Once I have those, I get R and P by modus ponens. Now we'll use our conjunction rule. It's a pretty simple proof, isn't it? Let's try another argument. How about C implies N and E? D wedges to N implying D, tilde D, therefore try to reach tilde C wedge P. Now before you start, I can see where we can get a tilde C out of this argument at some points. C is hiding up there in the first premise for us to get it out. But I don't see a P in this argument. I think what we're going to have to do at the end of this proof is use our addition rule for the wedge in order to get from tilde C to the claim tilde C wedges to P. So let's just concentrate on getting to tilde C. One step is going to be to use our disjunctive syllogism rule to get to N implying D. Now once we have that, we can get to tilde N through Modus Tollens because we already have a premise that says tilde D. Once we get to tilde N, look up there. We can, by simplifying premise number 1 using our conjunction rules, we can get C implying N and do another Modus Tollens. Once we do that, we've got our tilde C, and that's all we need to get to the conclusion of this argument by addition. Let's try another proof. Let's try one more example. This one's going to be a little daunting. This is a pretty complex premise, and so is this one. 2 horseshoe claims and some conjunctions, horseshoes, and wedges embedded in them. And C and tilde R will be our third premise, the simplest one. We're going to try to get to the conclusion that D wedges to R. Now, this is going to be difficult. We need a strategy, first of all. What I'm going to suggest is that R does not seem to be involved in these premises at all. In fact, the third premise pretty well openly affirms that tilde R is the case. What that tells me is I think we're going to have to prove that D is the case, and then we'll just use our addition rule to get to the wedge claim in the conclusion. So we need to prove that D is true to get this argument going. I'm going to use C first of all. I want to get that out by simplification because I'm going to use it on premise 1 eventually. But in order to use it on premise 1, I need to build it up a little bit. I'm going to build it up through addition so that we have something here that actually affirms the antecedent of premise 1. Having done that, I can move to the consequent thereof. Now, I've got a lot of dot claims to work with. Notice I can take the C that I got in 4, and I can take out that tilde P that I have in 6. That puts me in another position where I can put them both together through conjunction and affirm the antecedent of premise number 2. Once I do that, I have C implies D. I'm almost all the way home. I can use premise number or line number 4 to affirm the antecedent of line number 9, and that will get me D, and that's all I really need to get to my conclusion that D wedges to R. Well, this is some pretty tough stuff. I hope you guys have enjoyed my longest logic lesson so far. There's a lot here to digest, so I hope you guys spend a lot of time working on this particular lesson. It's still a crash course, and in covering propositional logic and natural deduction, we're just going to have 3 easy lessons, so digest as much as you can in each one. They're going to be the longest lessons I have online. We'll see you next time.